All right. So, good morning, everyone. I hope you're doing fine. I can see snow outside, but it's not very cold. I hope you're cozying up in your homes and enjoying the snow. First of all, are you hearing me fine? Perfect. Thank you so much. So, before we start the lecture, any questions, anybody? Anything that you wish to ask? We were in the last class doing the 7 principles of software testing. Any questions, anybody? You can unmute yourself or you can put the questions in chat. And by the way, just to let you know that the meeting is being recorded. Any questions, anybody? All good? You have your coffees with you? Nobody's sleeping? So, in the last class, we had started with the 7 principles of software testing. So we were doing these 7 principles, which were testing shows the presence of defects and not their absence. Exhaustive testing is not possible. Early testing saves time and money. Defects cluster together. Beware of the pesticide paradox. Testing is context dependent, and absence of errors is a fallacy. So out of these 7, we had already discussed the first 2, which is testing shows the presence of defects, not their absence, and exhaustive testing is not possible. Let's try to revise these before we move on to the next of these. So first, when it says testing shows the presence of defects, not their absence, it just means that it's almost impossible to test everything. You may not have tested all the workflows. You may not have tested all the environments in which the user is going to work. So just because you wrote some tests and all the tests are passing, doesn't mean you do not have any undiscovered errors. What you can, as a tester, do is just show due diligence by following a comprehensive test strategy, by creating your test plans, your test strategies, your test cases, and making sure to execute all those tests. You write good, honest, strong tests, make those tests pass, and whenever the user comes to say, well, I can see that there's a failure, you can always tell the user, well, I had a comprehensive test strategy, and according to the requirements that you gave me, I made sure that I tested all those requirements. But you have to tell the user that the user can never be sure that there will not be any undiscovered errors. So that is a disclaimer that you have to give to the user every time you deploy a product in the user's environment. And that is the reason why once you deploy a product or once you release a feature, it is very important to continuously monitor that feature. And to monitor that feature or to monitor that application, there are various tools that you can use. For example, for infrastructure monitoring, you can use the ELK stack. AWS also gives you a number of tools for infrastructure monitoring. You can definitely do things like surveys, or you can keep monitoring your applications remotely to make sure that all the features are running fine or the entire application is running fine. And if you see that there is some problem somewhere, you're able to fix that problem then and there. So there are a number of failure cases that we do discover after the product has been released. And one case that we discussed in the last class was Samsung Galaxy Note 7 defect. This was discovered after the release, and this happened because of a faulty third-party battery. So you can use ELK stack to continuously monitor your application, and this is specifically important for large-scale distributed applications where a number of errors or a number of failures can arise because of the inherent magnitude of the application, and it becomes difficult to have the application functional when you have such a high load, when you have millions and billions of transactions happening per second. That is where it becomes very difficult to handle the functional and the non-functional aspects of an application. So you have to make sure that you keep monitoring your application for any potential failures. The second thing that we did was to understand that exhaustive testing is not possible. And when I asked this question, there were a number of students who said, well, if it's a simple, small application, probably exhaustive testing is possible. So we did take an example of a simple, cute, small application. In fact, just one testable feature in that application, which was just, let us say, in print sum. And that was the only feature that we had to test. But because the inputs and the outputs, they were such a big range, so the input domain of this function, for example, was 2 raised power 32 into 2 raised power 32. So to test all of these inputs exhaustively, it would have taken us something like 600 years just to test this particular one testable feature. So some of you in the chat said, well, we could have a better server, or we could have a GPU, or we could have something in which one test does not run per nanosecond. Let us say we have 10 tests running per nanosecond. But imagine whenever you talk about testing, and whenever you go to your organization saying, well, I need more resources for testing, the first thing your organization will do is say no to you. Why? Because an organization, the basic mindset of an organization is that if you want to give more resources, well, give more resources to development. Because development will give you new features, better features, enriched features. And those features are going to make the client happy. Organizations are very hesitant to give more resources for testing. So if you tell the organization, well, the test runs for 10 transactions per second, but I want you to give me 2 more servers just to test whether the application is running for, let us say, 100,000 users per second. And each server is going to cost you something about $4,000. This means you're asking an extra $8,000 just to test one application's scalability. And normally, the organizations are not in a mindset to give you more resources just for testing. So, doing exhaustive testing is probably not a very good idea. You should do smart testing. So you should follow certain strategies to make sure that we're testing smartly rather than exhaustively. So consider a spreadsheet, for example. Consider Microsoft Excel. Now, this particular spreadsheet has hundreds of testable features. For example, we have text is a testable feature. Merge and center is a testable feature. All the menu items are testable features. What you see here in icons, cut, copy, format printer, bold, italics, underline, all of these are testable features. So there are hundreds of testable features here. Each testable feature is going to generate hundreds and thousands of test cases. And if you are to exhaustively test this particular spreadsheet, it may take you I don't know how many years now. So it is important to test complex applications having hundreds and thousands of features, but you should always make sure that you're following the right testing strategies to test these complex applications. So this was what we had done in the last class. Before I move on further, any question? All right, thank you. So now we come to the third principle of software testing, which seems to be a very obvious one, and you would have done that in other courses also, for example, software evolution or software development methods. But early testing saves time and money, and you would have experienced that while doing your co-ops or while making your personal projects. Understand that if you want to repair a defect, so the cost of defect repair is going to increase. I'm sorry. Yeah, is going to increase as the different phases move forward. So, for example, if you find out a defect in the requirement phase, it is going to cost you less. But if you find the defect in the design or the architectural phase, for example, let us say the example of, seeing whether the background color of a website is red or orange. So if you find that if not clearly understood the requirement in the requirements phase itself, you can always go and talk to the client that give me the RGB specifications. Which exact color do you want? So if you're going to discover that in the requirements phase, well and good. But if you do not recognize that or identify that in the requirements phase, the wrong requirement goes on to the design phase. So you've already written the requirement, you've already analyzed the requirement, you've already created a use case UML diagram from the requirement. Now you're in the process of creating, let us say, a sequence diagram. So a number of people here worked on that requirement. So there was cost of resources in the sense of cost of man hours. The resources were spent, time was spent, and now you've come to the design phase. Now, if you discover the error, it's going to cost you 3 times more than what it would have cost you if you would have discovered the error in the requirements phase. Similarly, if you do not discover the error in the design phase, but you discover the error in the coding phase. So what you're working with is a wrongly designed feature. And now you're trying to fix that in the coding phase. It's going to cost you 7 times more. Similarly, if you identify a defect in the testing phase, it's going to cost you on average 15 times more. And if you discover a failure when you've deployed it or when you're maintaining it, it's going to cost you about 30 to 100 times more than what it would have cost you in the requirement phase itself. So it's very important to do testing in all the phases so that you're able to discover error earlier on in your software development lifecycle phases. So testing early is really important, and that is why you have this concept agile. So in agile principles, what you basically do is that you have smaller sprints. They're about 4-week sprints, and you do not take all the features to be developed or coded or released in a sprint. You take about 4 to 5 features. You do the requirement analysis, you do the design, you do the test, you do the implementation, and you release a small subset of features. So that you do in small sprints, and you follow agile Scrum principles to make sure that you are releasing and deploying frequently, and then you're getting early feedback loops, and you can discover the defects early on rather than in software development lifecycle. We have the waterfall model. It's very to discover the errors. It's a very, very long process and very costly process also. So early testing saves time and money. So start testing as early as possible. Test the design guides. Get the feedback. The bugs are cheaper and easier to fix, and they would caused least damage. Now, the fourth testing principle is defects clustered together. This is particularly important and it's very interesting. Now, this is your Pareto principle. Pareto principle is an 80-20 principle. Pareto principle says that 80% of the defects are found in 20% of the code. So my question to you is, have you experienced the Pareto principle in your coding? And repeat, the Pareto principle says defects cluster together. So 80% of the defects are normally discovered in 20% of the code. So if you have a big code base, Pareto principle says, well, just take 20% of it and 80% of your errors are discovered here. So my question to you is, all right, perfect. So Fourier says, yes, one error triggers many subsequent errors. Yes, because most code is modular, so one mistake compiles. Okay, anything else that you can think of? What might happen in this 20% of the code? What kind of code would this 20% of the code be that I'm saying that this particular code is going to trigger 80% of the errors? Can you think about certain characteristics of a certain kind of code which can trigger errors? What kind of code will trigger errors? Codes that are dependent on each other. Good. So you have code which is having a number of dependencies. All right. What else? A bad equation which is part of other equations. Good. Anything else that you can think of? So any code which you think very good, constant changes. So any code which has a number of changes all the time, let us say whenever you're releasing new features, this particular part of the code has to be changed constantly. And that is the reason why it has to be tested constantly, because this is a piece of code which can generate a number of errors. Constant changes, badly written code, or which has a number of dependencies. Anything else that you can think of? Any characteristic of a code which makes it error prone? And if you think about the code that you have written till now, you would realize that yes, there is some 20% of the code which always causes an error, and the rest of the code is like normally not very error prone. So code reaching from changing database, yes. I would say any third-party integrations. So if you are, let us say, an online shopping website, and let us say for the payment methods, you are dependent on a third-party payment module, and if that third-party payment module has an error, then your code base will also have an inherent error. And sometimes there can be errors because of the integrations that you have with the third party. Anything else? So for people who probably, data structures that are not cleared between, so data structures which are not cleared between various parts of the code. So I'm not doing a good garbage collection. So garbage collection is not done properly. So when the garbage collection is not done properly, you may have leakage of memory. You may have a piece of data structure which is being touched by a number of different functions. And if you're not clearing the data structure, then the other functions may get wrong data structure. So if you have an array and it has let us say numbers 1, 2, 3, 4, one function goes and says, oh, I want to change this to 0. Now it doesn't clear this 0 to 1, but the next function comes and sees this as 0 rather than as 1. So yeah. So the garbage collection is not done properly. Environmental differences. Good. So there can be a number of environmental differences. What about legacy code? Is there anybody who has an experience with working with legacy code? So in your co-ops or in the jobs probably that you would have done, have you had an experience with working with legacy code? Okay, probably not. So sometimes what happens is that when you join an organization, you will probably not be writing code from scratch. You'll be maintaining the code which is already written by a number of other people. And sometimes that code is 100 years old. So it's very difficult to understand. There's no documentation of the code. The code is just sitting there doing its job, and other pieces of code are built on top of it. Nobody knows how the legacy code works, and you're not allowed to touch that legacy code, because if that stops working, the entire stack stops working. So it's on that thin piece of legacy code that the entire application is standing. And nobody knows how that legacy code works. But if something goes wrong with the legacy code, your entire application suffers. So it's very important to make sure that you're testing the legacy code well. And that legacy code might be just 20% of your entire code. So yes, you're right. There can be a number of ways in which a code can have a number of errors. And normally we have about 20% of the code which can have 80% of the errors. So if you have very complex components which have a number of dependencies or which are changing the most, or if you are inheriting legacy code, if you have third-party dependencies, if you have volatile modules, those are the code modules which will have 80% of the code, 80% of the errors. So these 20% of the code places are called hotspots. So anything which is legacy code or which has different teams or different functions touching the same part of the code and not doing their garbage collection and not making sure that they leave that part of code in the original form, or the features are suffering many changes, or there are some fickle third-party integrations. If you have that kind of a situation, that 20% of the code can generate 80% of the errors. So it's very important to look at that piece of code and make sure it's documented well. And every time you introduce a new feature, you make sure that you go to that 20% of the code and test it correctly. And there are a number of things that you find in organizations like IBM. So IBM, for example, had the IBM Rochester product, and that had about 80% of the errors in two components, INTs and INIT. So the third principle is beware of the pesticide paradox. And this diagram shows the pesticide paradox. The pesticide paradox, before I come to understanding the pesticide paradox, my question to you is, you write certain test cases for your code. Do you need to change those test cases in the future? So you have a piece of code, you write test cases for your code. So my question to you is, do you need to Oh, yes. So if the code is updated, yes. If the code is updated, then you write new test cases. Anything new? So the point is, if you're not writing new test cases once a code is updated, uh, how it depends on how the code updates. Lou, how does it depend on how the code updates? Don't you think that whenever the code updates, new test cases should be written to make sure that the updations are successful? Do you think it is dependent on the way the code is updating? If the output of the parameter of the code does not change, wonderful, wonderful thought. Uh, no, you're right, but a good tester make sure that everything is tested. So if there has been an update, even if the output of the parameter of the code does not change, a good tester will make sure that the update has not introduced any more errors. So it's very important to have some changes in the test cases so as to make sure that the original component or the original code did not change. See, we live in a dynamic environment and the code may be updated all the time. You're releasing new features, the client expectations are changing, the market expectations are changing. So you're always updating your code. And when you're updating your code, you have to make sure that you're writing new test cases for the code. And if you're not doing that, then you are affected by something called a pesticide paradox. A pesticide paradox means that if you continue using the old test cases, then these old test cases are not going to discover new errors in the code. And your job as a tester, your KPI as a tester is that you keep discovering new errors in the code so that the user does not discover a failure and the user does not get a bad user experience. Not just that, a tester is also encouraged to have, let us say, new people in the organization or people who do not belong to the same domain to look at the test cases and give the tester new perspectives. Let us say if a tester is a domain expert also, for example, most of the testers are software developers also. They understand the software domain. But let us say if there is a client who does not know about the software at all, and if they start using the application, they may have a different perspective to using the application and looking at the way they are using the product. The tester may have a different viewpoint on how to create new test cases. So a tester is always encouraged to think about new and better test cases so that they're not caught in the pesticide paradox where the test do not discover new errors if they are there in the code base or in the application. So make sure that you are reviewing your tests, you're modifying or adding to your test scenarios to make sure that any defect in the application is discovered. So whenever there's a new release which is made, then make sure that the old test cases are passing and you also write new test cases. This is something called regression testing, if you are aware of regression testing. So regression testing just makes sure that if something new has happened, you make sure that the old test cases are passing and you also make sure that the updated test cases are passing as well. So make sure that you're writing new test cases, you have new ideas, you can request opinion of other testers. You should know about the product, you should explore other ideas to make sure you are discovering any undiscovered errors. The sixth principle is testing is context dependent. Why do I say that? Why do I say testing is context dependent? For that, I'll show you this particular diagram. What do you get out of this diagram? So when I say testing is context dependent, this diagram explains it all. This is interesting. Do you know what this is? Do you know what this is? Okay, somebody in the chat says, oh, Docker, yes. Good. Yes, these are different type of containers, and all of these are containers. So these are ship containers, these are Docker containers, which are used for increased scalability and containerization of your applications and microservices, for example. This is a different container which you bring to the university every day to have your lunch. And these are containers in which you probably store your tools or your books, etc. But all of these are containers. They're containers in different contexts. And when you're writing test cases to test whether these containers work properly or not, all these tests have to be different. So for this, you're writing software test cases. For this, you're writing test cases to make sure this is leak-proof. For this, you're writing test cases to make sure this does not break. For this, you're trying to write test cases to make sure that these are rust-proof. So in any case, you're writing test cases, but it is very important for a tester to understand the domain in which you're writing the test cases. So sometimes what's going to happen is that, let us say you're trying to write test cases for an application which you do not understand. For example, if there's something related to the human genomic sequence, and if you've always done software in your life and you do not understand a lot about human genome and the DNA sequences and the ABC kind of genome and how the entire cycle of the DNA gets formed, you will not be able to write these cases for this. So it's very important for you to understand the application, what the application does, what is the domain, to make sure that you're writing the right test cases for that particular domain. So that is why I say that testing is context dependent. So before you start writing the test cases for an application, make sure you understand the domain and the context of the domain. The last thing that I'm trying to discuss is that absence of errors is a policy. Now, absence of errors is a policy. What that means is that if you think that your test cases are passing, doesn't mean that your application is defect-free. You always go back to your requirements. And you have to make sure that the application is running as per the requirement. So, application running correctly does not mean that it's passing all the test cases. Running correctly means it has to be running according to what the client wants, according to the requirements the client has given. So if there's this absence of errors, that does not mean that the application is running correctly. You have to go back to the requirements, to what the client wanted, to make sure that your application is running according to the client requirements. Okay, I have something in the chat. Isn't that the same as principle 1? No. So principle 1 says, let's come to principle 1. All right, principle 1 says, testing shows the presence of defects, not their absence. So principle 1 and principle 7 are related but different. So principle 1 says you may not have written all the test cases to make sure that your application is defect-free. So you may not have that. You may not be doing the continuous monitoring of your application after the release, or you may not have thought about all the application scenarios. So, so you may not have written all the test cases. But the seventh principle says that when you're writing the test cases, you go back to the requirements and make sure that that you're writing all the test cases according to the requirements. So if your application is running properly without any defects, doesn't mean that your application is running correctly, but because correct is according to what the client wants. So this is how these two things are different. In the first case, you're not writing, you cannot think of all the scenarios. So if the application does not have defects, that does not mean that it may not have defects while it's running, or you may not have written all the testing scenarios. But the seventh principle says, go back to the client, go back to the client requirements and see whether the application is running correctly according to the client or not. That's how they're different. Any other question? So these were the 7 principles of software testing. So just go through these 7 principles and see if you have any issues, and then we go on to the next topic. Any questions, anybody? Otherwise, we move on to test-driven development. Are you fine with the lab? Are you fine with the labs? Is everything fine? Is everything going okay with you? Anything that you wish to discuss? All right, if there's nothing, let's start with the next topic, which is TDD and PDD. And for this, I encourage you to read chapter 8 of the textbook. It has a great context on test-driven development and BDD, which is behavior-driven development. So you're encouraged to start reading the textbook now. And we'll have the first midterm in February. So you have about a month and half a month to start reading the textbook, to start going through the slides, see what we've done till now. If you have any questions, come to me and ask those questions. Okay. Something at the PDD and PDD slides are not posted. I'll post them today, but the principal slides are already posted. Yeah. Any other question? Perfect. All right. Thank you. So now we come to the test-driven development. The test-driven development says you develop code driven by tests. So what that means is simply that you go to the client. So normally a business administrator goes to the client. The client gives a set of requirements. Once you get these requirements, then you develop test cases from these requirements. When you develop test cases from these requirements, then you write code which is just enough to pass these test cases. So normally, what you would do is, now the strategy of writing code is now shifted from the developer to the tester. I'll tell you how. For example, let us say the client says, I want an online website environment in which I want a login feature. I want the cart feature, I want the wish list feature, etc. So let us say the cart feature, you write various test cases. The test cases can be, am I able to add products in the cart? Am I able to remove products from the cart? Am I able to view the cart. So let us say these are the three features which are identified during the requirements. Now the tester goes through these features, and for the add feature, let us say writes test case 1, test case 2, test case 3. So the first test case can be, well, I added 2 items from grocery, and are these items added to the cart successfully? The second test case can be, well, I added 5 features. Third can be, well, I added 10 features from different categories. So this is how I'm writing the test cases. TDD says, run these test cases. So when you run these test cases, obviously they will fail because there's nothing in the code to run to have these run successfully. So some people would come and ask me as to what is this seems very ridiculous. Why do you need to run these test cases when you know they are going to fail? But this is a principle of TDD that you write a test case, make it fail. Now you write only enough code to make that one test case pass. So this is how TDD runs. Write a test case, watch it fail. Write just enough code to pass the test. Run the test again, make it pass. And then you have the third phase in the TDD, wherein you refactor the code. Refactoring basically means that you can improve the code without changing its behavior. So let us say you added a few items in the code. You added a few items in the cart. You wrote a test case for adding 2 grocery items. You run the test case, you make it fail. Then you write only enough code so that you're adding only 2 items in the cart. These 2 items have to be grocery items. And then you run the test again. And then when the test passes, then you can improve upon the code. Improving of the code means you do not change the behavior of the code. That means you're still adding 2 grocery items, but you can improve the code. For example, you can increase the readability of the code, or you can optimize the code, or you can probably add a few data structures, or improve upon a few data structures, or improve upon the time complexity or the space complexity, etc. But you're not going to change the behavior. It is still adding 2 grocery items. So when you do that, this is called test-driven development. Why it is called test-driven development is because the development of the code is driven by the tests written for testing the features of the application. So this is test-driven development. And you're writing the code depending on the test cases written to test the features of the application. If this was not there, how would you implement the add feature? You would know the requirements. The requirement is in the cart, you have to add items. You do not have test cases right now. You have test cases after you've written the code. So when you start writing the code, and this is why TDD came into existence, because the coders had different skill sets. The coders had different ambitions. And the coders would think about solving an application in different ways. See, we're human beings, we're not robots. We do not all work in the same way. So I would think of adding in a cart, let us say I'm thinking about, well, I have some 80 80 categories in the add cart feature. I would write a big code base to implement adding in the cart all 80 category items at once. This is going to take me a lot of time when I'm going to implement my code, when I'm going to write my code. And for these 80 category item insertions in the cart, I would need a number of test cases in the end after I've implemented the entire big code base. So writing the tests at that particular time, executing the test case on such a big code base, and then making sure the code base runs correctly is a big, big task. And that made applications fail. There had to be a process in this madness. So for that, we introduced TTT. Only bite what you can chew. So we encouraged you to bite small chunks. So in that particular case, TTT encouraged you like this. Going for a feature. Think about the various test cases for that feature. Run those test cases, make them fail, then write only enough. And this is a big thing, enough. Write only enough code which can pass one test case. And then refactor the code without changing the behavior, optimize the code, have it in a better time complexity, or make it more readable, more understandable, but do not change the behavior. And then go on to the next test. If you do something like this, then you have a testable code. Every time you write a single piece of line of code. So that made the code base smaller, more testable, and more easier for the testers and developers both. Okay, something in the test. Unrelated question for those of you who missed the lab last week, do we still need to submit? Yes, you still need to submit. If you missed the lab, you have to submit. Please talk to the lab TA. You have the lab document on the Brightspace. Please go through the lab document. If you have any problems, please contact the teaching team. We should be able to help you. And you are going to submit to the Brightspace, otherwise you're going to lose grades. So yeah, please submit. Any other questions? So this basically is test-driven development in a very simplistic way. Is there anybody who doesn't understand TDD in this form? Are you able to understand what TDD is? Any questions, anybody? Okay, I can't see anything in the chat. All right, so this is how you play the TTT game. You're not allowed to write any production code unless, okay, so you're not allowed to write any production code unless it is to make a failing unit test pass. And because you're writing only for one feature and for one unit for that feature, that is why TTT encourages you to start with unit tests. Once you've written all the unit tests, then you go on to the integration test, and then you go on to the end-to-end system UAT test. So you're not allowed to write any production code unless it is to make one failing unit test pass. Then you're not allowed to write any more of a unit test that is sufficient to fail. And you're not allowed to write any more production code that is sufficient to pass one failing unit test. So point is, you write a test for a feature, make it fail, write just enough code to pass the test, and then improve the code without changing its behavior. So test-driven development is basically a software development technique that entails writing automated test cases earlier than writing functional pieces of code. So this finishes with the lecture for today. In the next lecture, I'm going to explain TDD using a Java program and JUnit test. So that is why I introduced JUnit beforehand, because for TDD, if you want to have a demo in TDD, you cannot have the demo unless you know Java and how JUnit works on Java. That is why JUnit was done before TDD. So in this particular lecture, we started with the continuing the 7 principles of software testing. We'd already done 2 tests, 2 principles before. We finished with the last 5 principles. Once we finished those 5 principles, we started with test-driven development. Test-driven development is basically a methodology of software development where from features you write the test cases, and those test cases then drive you to write code, which is just enough to have one failing unit test pass. Thank you so much, everyone, for attending this lecture. If you have any questions, please do not hesitate to email me, and we'll meet again on Tuesday now. Thank you so much. Bye.